Okay, so we were on the topic of de Broglie relationship of the particle and wave duality of moving particles. Okay, and the next topic we're going to discuss here, okay, is about light spectrum. Okay, and we're gonna introduce a couple new concept first. The continuous spectrum and the line spectrum. Okay, so first of all, what is the spectrum you talk about? Okay, spectrum is a collection of electromagnetic radiation. Okay, collection of electromagnetic radiation. Okay, and now what do you mean by continuous and line? Okay, well, continuous spectrum. Okay, yeah. Although this sounds like a new concept, okay, but everybody actually have seen continuous spectrum in real life. Okay, yeah. Summertime after rain, there's a good chance that you see rainbow, okay, in the sky, okay, and with all kinds of colors, okay. How did that happen? How did rainbow happen? Okay, in simple words, okay, rainbow is a continuous spectrum, okay, because it's going from red color all the way to violet color, right? And in that range, okay, supposedly the color is gradually changing, okay? So a continuous spectrum is a collection of electromagnetic radiation in a certain range. It contains every possible wavelengths, frequency, or energy of radiation. Okay, now, so if you remember when we first introduced the electromagnetic spectrum earlier, okay, right in the middle we say this region is the visible region, okay, and here is your red end, and here is your violet end, okay, and the rainbow pretty much go from the red all the way to the violet, and within that range, okay, it has every possible frequency, wavelengths, energy covered. Okay, so if we're showing them on the electromagnetic spectrum, okay, a continuous spectrum is a band. Okay, yeah. So in this region, we have every possible. Or you could have another region that you cover an entire band. Okay, that would be a continuous spectrum. Okay, when the rainbow is the visible part of the sunlight going through, okay? And you've all seen prisms, okay? A triangular shaped glass where if you have one beam of light, okay, and mostly sunlight or white light going through it, and you see it, if you have a screen here, you ended up getting rainbow color on the screen, right? Now, so white light or a combination of different radiations, okay, goes through the beam and then goes through the prism and then being separated, okay, or not separated, being kind of going from a mixture to an orderly line up of different color, different wavelengths, frequency, okay, now, and the sunlight, okay, is a typical white light that contains continuous spectrum, okay, and that's why it can break into rainbows, okay, from red color all the way to violet color, every single color in there you can see, okay. Now, what about this line spectrum? Okay, yeah. If you have a tungsten light bulb and if you lead that light through a prism, okay, and put it on a screen, okay, then you're gonna see the difference. Doing that, you will not get a rainbow. Okay, why? Because it doesn't, the light, okay, the radiation coming from a tungsten light bulb. Okay, so tungsten light bulb. Okay. Because the light, okay, the electromagnetic radiation coming from a tungsten light bulb, okay, is not a continuous spectrum. Now, if you find out what kind of radiation, okay, are in there, okay, this is what you're gonna see on a spectrum. You would see, okay, this beam of tungsten light bulb light contains, okay, well, this particular wavelengths or this particular frequency of radiation. Okay, it may be a particular color, let's say like, you know, light yellow color. Okay, and then it also might have another different color in it. Okay, and within the visible region it may have these two colors, but then outside of the visible region you could also see, oh, okay, there's another radiation that's mixed in there. Okay, so a continuous spectrum is made up by numerous different electromagnetic radiations that's all grouped together in a certain region. Okay, but a light spectrum is just a collection of specific electromagnetic radiations that are not continuous with each other. Okay, all separated. Yeah. So you see band here, okay, with all the possibilities, but in line spectrum, you only see these lines in the spectrum. Okay, it contains only a few frequency wavelengths and energy available in a certain range. Okay? And now, from outside looking in, you see, well, the tungsten light bulb light, what's the difference of it with sunlight? Well, scientifically, this is the biggest difference. Now, sunlight belongs to continuous spectrum, okay? It contains technically, all the possible wavelengths, frequency, rate, and energy, different kind of photons available in an entire range, okay? And light bulb, tungsten light bulbs, okay, it doesn't have all of that, okay? It only have a few lines on the spectrum, a few specific frequency, wavelengths, and energy. Why? Why does atoms, why does tungsten light bulbs only give a few specific wavelengths? And if tungsten does this, okay, what about other metals? Okay. Now, when people found out this, okay, about the line spectrum, they already know that the light bulbs are giving off light because when you put high voltage electricity on it, okay, the electrons within those metal with tungsten, okay, goes through, okay, energy change, and as they lose energy, okay, the energy of those electrons, okay, as the electrons goes down in energy, those energy were released in the form of a photon, okay. And it's not just tungsten. People have tested this on almost every metal out there, okay. The result is you may get different lines, okay, but all different atoms, okay. Atoms gave line spectrum when external energy is provided. Tungsten can do this, iron can do this, many different metals can do this. And they might give different spectrum, okay, but every single one of them gave line spectrum. Only a few specific energy, frequency, and wavelengths are available in the light coming out of metal when you provide energy, like when you put electricity on those metals. Why? How do you explain that? Yeah. We already know what happened, how the light comes, okay? People at that point already know, okay? The electrons within those metals, okay, took the electricity energy, okay, but at some point, those energy that they took, okay, they would eventually take it off. And when they get rid of those energy comes out of the metal in terms of a photon. But why only some photons? Because each of these lines are representing a particular type of photon, right? Yeah. If these electrons are giving off energy, shouldn't they be giving off their energy freely, however much they want? Shouldn't they go down whatever amount of energy they'd like to? And if that's the case, then they really they really should have a continuous spectrum with every possible energy, frequency, and wavelengths available. Because let me try to draw this out. So let's say this is your electron. After absorbing, like originally, let's say it's here. Okay, it absorbs some energy. Let's say it go all the way up. Okay, and then it's going to release energy to the outside. So technically, it can go down here. Then it's going to give off this much of energy. If it's going down, then this much of energy is going to be released as a photon. And then it could also go down this much. It could also go down this much. It could also go down this much. It should be able to go down wherever, however much energy it wants to, right? And if that's the case, then I should have from 0 to delta E, every energy between that, value between that, is possible. So shouldn't atomic spectrum be a continuous spectrum? Why is it not? It feels as if that your electrons are not going all over the place. Instead, after the electron goes to a higher energy level, it feels like, okay, you can only come down here, and then you're going to give off this much of energy. Okay? Or you could only come down here, and then you would give off this much of energy. Or you can come down here, and then you would give off this much of energy. So delta E1, delta E2, delta E3, and that's it. Each of these would be representing one of the lines. Okay, now, before, people's understanding is they can go wherever they want, however much they want, all over the place. Okay, but then people found it's actually, no, only these, let's say, in this range, these three possibilities. It doesn't go to other energy. Well, who decides that? Why? How can this be? Yeah. Okay. But regardless of how you explain it, this is the fact. Every atom does this. Okay. The conclusion that people can draw from here is that there are only certain energy levels of electron allowed in an atom. It can only go to these places. For every atom is a different set of energy level, but nevertheless, everybody have their own set of energy level they can go to. Okay. And once the values are set, now your electron can't say, I'm gonna go here. Can't happen. Your electron can't say, I want to go down this much. Can't happen. You either go down here, okay, or you can go down here, or you can go down here. And as you go down that much, the energy released gave you a specific type of photon. So, first photon can be produced H nu 1, second photon can be produced H nu 2, the third photon can be produced H nu 3. Okay? So it feels like only these energy levels are allowed in this particular atom. Other places, your electrons can't go. And people call this that atomic energy levels for electron is quantized. Okay. No. If you're having trouble understanding or having trouble picture what I'm talking about here when we're talking about electrons, okay, let me see if I can give you an easier metaphor. Okay. Imagine that you have an endless set flight of stairs. Okay. And imagine you throw a ping pong ball on this flight of stairs. Okay, so a ping pong ball is thrown onto the stairs. What's going to happen now? Your ping pong ball is going to bounce around, falls down, and at some point, because let's say the flight of stairs is endless. Okay, so at some point, your ping pong ball is going to stop, right? Do you expect the ping pong ball to, let's say, stop right here? Of course you don't. You're not crazy. Okay? This ping pong ball is not going to float in the air. So where do you expect your ping pong ball to stop? Well, maybe here, or maybe here, or maybe here. Okay? On one of the stairs, right? Now, the stair, the flat part of the stair, okay, with each individual height, okay, this is the only place that your ping pong ball is going to end up to be. Now, that everybody can picture, right? No. Okay, now view these ping pong balls as electrons. Okay, and these stairs as the energy level within an atom. Okay, so energy level within an atom, okay, is quantized. Okay, electrons, so ping pong ball can only stop on one of the stairs. one step of the stairs. Okay, and electrons can only stay on one of the fixed energy levels in an atom. Yeah. That's what it is. Okay, and eventually people start to order these energy levels. Okay, now, they say the lowest energy level, okay, where when your atom is the most stable, okay, for each electron, they call it, this is E0 or ground state. Okay, and or let's start with E1. Okay, ground state, and then the next energy level it's going to go to, okay, is E2. Okay, and E2 is your first excited state, because your electron need to absorb more energy to get there. Okay, getting more energy for electron, we say the electron is now excited. Okay, and then the next one, okay, is so excited state number 1, excited state number 2, so on and so forth. Okay, and this also explained why, like, only when you provide enough energy, your electrons will be excited. Because if you only provide, let's say, if there's only enough energy for the electron to come here from the ground state, what do you think the electron is going to do? The electron is going, I'm staying on ground state. I'm not wasting my time. I can't stop there. Like a ping pong ball can't float in air. I have to get here, at least. Or if you have more energy, I could also get there. Or if you have more energy, I could even get here. Okay? But I'm not staying outside of these energy levels. I'm not staying anywhere in between. Okay? And once they got excited, when they come down, let's say if it goes from E4 to E3, then this much of extra energy, okay, because you're losing energy. Where did the energy go? The energy could leave this electron, this atom, in the form of a photon. Okay, it could also go from E4 to E2, and it's going to shoot out a different photon this time. So H nu 1, let's say H nu 2, and this H nu 2, obviously, because it's jumping from 4 to 2, it gave away more energy, so that photon would contain more energy. It could go all the way down to E1 as well. Okay, and now this time it's going to give out a high energy photon. Okay, so this is people's conclusion on how the different energy state is allowed within the atoms for electron. Okay, and eventually they figured out for a particular atom, okay, they actually have a set of equation to calculate. You don't need to memorize this equation. We're not using this equation to do any calculation. This is just kind of for your reference. The n's energy level, okay, would have the energy of negative 2.178 times 10 to the negative 18th joule, and times z square over z is the atomic number, so the more energy, the more nucleus, the more protons you have in your nucleus, the higher the z is, and the higher the z is, the larger value En would be. Okay, yeah. And square. Okay, and you can see this relationship for each individual atom, okay, then you know your z value, okay, and as your n increase, okay, your energy value, okay, is going to become smaller and smaller and smaller, okay, and eventually, as your n approaches infinity, so this E goes all the way up to En. As your n approach infinity, okay, then En should approach value of 0, okay. So that's the highest, and then as you go the highest energy, and that's a free electron, okay, it has no relationship with the nucleus anymore, okay, and that's when your n is approaching infinity. And at that point, because the electron has no relationship with the atom anymore, we say the energy there is defined as 0, okay, and everything else, okay, is below it, below 0, so that's why you have the negative sign there. Anyway, now the point here, so as n approaches infinity, En value approaches 0. So that means electron becomes free and out of control. And with this energy state, what good does it do? Okay, this provides us with a way. When an electron jumps from a high energy state to a low energy state, the emission photon energy can and frequency and wavelengths can be calculated. How do you calculate it? If it jumps from a higher energy level, En, to a lower energy level, Em. Okay, then this delta E between them is your energy difference, and then that should equal to the emission photons energy, which is h nu. Okay, and plug this equation within into now this setup, or that could also equal to hc over lambda. Okay, so plus this equation in. Now, for z, okay, our people's original study, okay, is obviously you want to study something, you better start from scratch. So you better start from easy. What's the easiest z value? Well, it's 1. It's hydrogen atom. And that guy has only 1 electron in it. We can focus on that 1 electron. Don't worry about the other electron being affecting it and all that. Okay? And now, when you take z equal to 1 and then you plug this equation, okay, this definition into this setup, En minus En equal to hc over lambda, and rearrange the equation, eventually you would get an equation that can help you calculate the emission photons wavelengths, knowing which energy state you were dealing with. And that equation looked like this: R over m square, 1 over m square minus 1 over n square, okay, equal to 1 over lambda. And the R, is called the Rydberg constant, and this equation here is called the Rydberg equation. Using Rydberg equation, we can calculate every line in hydrogen spectrum. Okay? And no, let's see. How do we use this equation? Well, for the Balmer series in hydrogen spectrum, m equal to 2. Okay? And if emission photon has wavelengths equal to 486 nanometer, what is the m value? Oh, okay, for the Rydberg constant, I forgot to put the value here. 1.097 times 10 to the negative second nanometer to the negative first. Okay, now, all right, coming back to the example. Okay, what do you mean by this? Okay, now, well, let's think about the hydrogen spectrum that we just talked about. Okay. Since it's only one electron, so we have only one set of energy levels. Okay, and let's label them as 1, 2, 3, 4, 5. Okay, the Balmer's theory. Now M, remember, because the energy levels have defined negative energy values. Okay, so M here is actually your endpoint. M is in the Rydberg equation is where the electron jumps down to. So in what energy level would you be able to jump down to 2? Well, you could be in energy level 3 and you jump in 2. You could be in energy level 4 and you jump to 2 and gave a photon. You could be in energy level 5, you can jump to 2 and give off a photon. 1, 2, 3, and possibilities endless. You could be in energy level 6, energy level 7, energy level 8. Each of these jumps to energy level 2, okay, represents a specific line, okay, in the hydrogen spectrum. Okay, and then of course, M, if you use M equal to 1, you would have a different series of lines, jumping from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, whatever. If you use 3 as M, as where your electrons are jumping to, okay, then you could have electrons jumping from 4 to 3, 5 to 3, 6 to 3, 7 to 3, and you would have another series of line within the hydrogen spectrum. Okay. Once we establish all this, I'm not really worrying too much about a calculation, because the calculation of Rydberg equation is always plug and chug. Okay, so (1.097) times 10 to the negative second, okay, times 1 over m is 2, so 2 square, minus 1 over n square should equal to 1 over 486 nanometer. Now, this is nanometer to the negative first, and this side you also have nanometer to the negative first. So those two units cancel each other. So you should only deal with numbers. And now, multiply the number, rearrange, put your n square on one end, and eventually you find in this calculation, your n square equal to 16. And that means n equal to 4. Okay, what does that mean? Well, when your electron jumps from energy level 4 to energy level 2, you will have a photon emitted, and that photon's wavelength equal to 486 nanometers. Okay, and this is one of the many, many lines within the hydrogen spectrum. And how, well, then the question comes as, how do you know all this is valid? The whole thing sounds so abstract to me. Well, let's put it this way. People have been able to accurately, identify every single line in hydrogen spectrum, okay, and the measurement of the real deal and the calculation, okay, from Rydberg equation has been an unbelievable match. The actual lines, the actual emission photons, frequency, wavelengths, and energy match so well with our calculation from the Rydberg equation. And actually, there are certain lines people didn't know or couldn't observe before. But the Rydberg equation could easily predict. And then later on, with improved technology, people were able to find, oh, we calculated there should be a line here. We were never able to observe it, but now we have better technology, and that line is right there with that particular frequency, wavelengths, and energy. Using Rydberg equation, we could predict the things we didn't observe before, and that's where it convinced people. Okay, this model works. As abstract as it is, the model seems like it works fine. And again, every single line in the hydrogen spectrum at this point, okay, well, close to every single line of the hydrogen spectrum that people can observe at this point matches very well with the Rydberg equation results. All right, so of course, hydrogen is the simplest element out there. Only have one electron, easier to study. What about the other elements? Are their energy levels still line up like this, or do they, when you have multiple electrons, how do you put them into these energy levels? And that's going to be our topic for next class.